All right, so let's get into stats or analytics, depending on how you want to call it. So, the idea of this particular section in video is to cover some things you might already know, but to do it in a slightly different fashion, which is just talking about it more, how you might talk about it in business applications, and just to get the basics down. So, when we talk about analytics or statistics, we're usually just trying to find information in the data. Some of the most simple ways to go about that is to run some basic descriptives, meaning that it describes what's going on, with the most common being what we call measures of central tendency. All that is where's the middle? Where does the middle happen to be at? Most common way to do this is to get what's called the average. It's also called the mean. And that's the one that we probably see the most of. I think that the average gets a little overutilized, in my opinion, because the average really does need other information to help it make sense. But the average is just add up all the values, divide it by the total number of values that you have, and then that will give you a nice potential measure of where the center might be. Another measure of center is the median, and that's just saying if I lined up all the things from small to big, what's in the middle? And mode is whatever happens the most common. These are all great metrics and quite frankly, still tell us a lot about what's going on, but they don't always give us the full picture. So for example, let's say that you are getting a job. It's a job you really need. You're super excited. And you get told that there are actually two of the same position available within the organization in two different departments. And you can either join Department A or Department B. Your tasks, your job, everything would be exactly the same. The only difference is the manager in that department actually sets the salary for each person. They have a certain amount of budget that they use. So would you care which department that you're in? Department A pays employees on average $150,000 a year. Department B also pays employees on average $150,000 a year. If all you were told is Department A and Department B both pay on average $150,000, you'd think they were the same. But look at that data. Do you have an opinion? Do you think it'd be better to be in Department A? Do you think it'd be better to be in Department B? And feel free to answer. Nobody can hear you, so feel free to answer out loud if you like. You might have an opinion. Depending on how you interpret the information of the details in this table showing the salaries of each person in each department, you might feel that Department A is a better choice, with the reason being that there are a greater number of people in Department A who make $150,000 or more in that group. So depending on how you interpreted that, A might be the better one. You're more likely to get at least 150 or more, because in B, there are actually only 3 people who get 150 or more. Now, some of you might have said, no, Department B is better. And your brain goes straight to, they pay up to 260 in Department B. You're already jumping straight to this idea of how spread out the data is and with things at the top and things at the bottom. The point here isn't which department's better, because that's actually very hard to say. The point is averages lose a lot of the additional emotional part that we might feel, especially in something like people analytics, where different people have different risk tolerances in terms of how they would approach joining one organization or the other. So when you use something like an average, you sometimes lose the complexity inside the data itself. The more of these measures that you can use, like adding the mean, also showing maybe where the median is, where the middlemost value is, as well as the range, can really help to show it. Another thing to talk about that comes up a lot is outliers. So some might notice that 260 in Department B could be what we call an outlier, meaning even though one person makes that much, no one else does. So maybe that is skewing the average. When you look at the other individuals, they don't on average make 150. And depending on how you approach outliers, you might feel differently about it. Now with people analytics, you have to be careful with outliers. Sometimes there's this belief that outliers are what we toss out. They're the thing that skews the data. But in people analytics, sometimes an outlier is the story. So always check the data out. Always look at ranges, always look at differences, see where you might have something going on because there could be something of particular note. So for example, maybe there is a role within Department B that holds a much higher scope and range than the others, and that's valuable information. So outliers, yes, they change the makeup of the data, but oftentimes they're part of the interesting point of the data set as well. Something else that we need to think about when we're diving into analytics is this idea of population versus sample. So a population is when you have all the data on everybody that you care about. A sample is when you only have a small set of the data on everything that you care about. So if we were evaluating an organization and we had data on all of the sales employees, if all we were focusing on were sales employees, well, we'd have the full population. Cool. If the only data we had was sales employees, but we were trying to assess the entire organization, well, we'd only have a sample. And in fact, we'd have a sample very specific to the sales department. So population sample is just a question of what you're trying to measure. It's not a question about the data itself. So depending on the group that you're trying to focus, you might be able to have access to the full population of data. You might only be able to access some of it. Maybe you have information you want to gather, but the data's missing, or you're not able to gather it on some people. You might by default only have a sample. The reason that I bring this up in the statistics analytics portion is it does actually change some of the math that we use sometimes. And so I just want you to be aware that some things are affected by the idea of whether we have a population or a sample. And that starts to come in with certain calculations here. So your range is the smallest number to the biggest number, helps give a good sense of where it's at. And it's the starting point to this concept around variance or standard deviation. We call these the measures of spread. It's basically how separated or how squished together all of your data points are. And this is an incredibly useful set of data. When I first started doing analytics, I skipped this a lot, only to then realize that you really need to understand how dispersed the data is in order to get a full picture of it. So range is just small to big. Variance is like how much does each point wiggle around the average? And then standard deviation is this extra bit of math that we do on variance. And what it lets us do is have a common, consistent way to think about how spread out our data is in context to itself. So standardizing to use a standard deviation lets us look at things in a common, consistent way. If you run the math on variance, you're going to end up with a weird number, and I'll show it to you here. So here's what the actual math looks like. Range is really simple. Take the biggest number, subtract the smallest one, you've got a number of how spread out the data is. Variance, and you'll notice there's two different equations here, one for population, one for sample. Variance just says for each data point, how far away is it from the average? So for data point employee number 1, it is 1 minus 8.4. 8.4 happens to be the average of this data. And then we square it so that we can get rid of any negatives, because something's going to be below the average, something's going to be above the average. If we do that for every single data point, and then we divide it by the number of data points we have, we get a value, which is the variance. For these particular 10 pieces of data, it happens to be 47.64. And I bring this up because 46.64 is like, what do I do with that? I have no clue what that number would even mean. I'm looking at a table that shows me time with companies in years. So employee 1 has been with the company for 1 year, employee 2 has been with the company for 22 years. 47.64 makes no sense to anybody. But it is how far away is each individual's point from the average. We can take that value and turn that variance into a standard deviation simply by getting its square root. When we take 47.64 and we square root it, we get 6.9. 6.9 is the standard deviation, and we can talk about that in the same format as the data itself. So we can say that the standard deviation is 6.9, or almost 7 years. So we now know that the average is 8.4, but that the spread, meaning how far each individual employee is from 8.4, that average number of years, is about 7 years. That's huge. That means my average is 8.4, but like most people are either 7 years that way or 7 years that way of it. And that means that there's not a lot of people there, which if you look at the data, actually does kind of make sense. If you walked into a room with these 10 employees and you said, "Hi, everyone. I'm so glad to be here. I know that you've all worked for the company about 8.5 years, right?" Employee number one is going to look at you like you're insane. They're like, "I've only been here a year." Employee number two is going to look at you like you're insane, saying, "I've been here more than 2 decades." 8.4 is not representative. If you knew that the standard deviation meant that most people are a good 7 years from your average, well, that helps you get a sense of how accurate the middle point may or may not be. Now, you'll notice I gave you 2 definitions, one for population, one for sample. The only difference between the definitions is this population one is divided by 10 because we have 10 data points. This sample is 10 minus 1. And I'll give you a second to think about it, but why is the math different? Why do we do 10 versus 10 minus 1? Feel free to talk at your computer. Nobody can hear you. So the difference is that in a sample, we don't have all the data that we want to have. In a population, we have data on everyone we care about. So the average and the variance and the standard deviation for just these 10 people, if they were all we cared about, we know the answer because we have all the data. We can calculate it. It's 6.9 years is the standard deviation for the population. And I have all the data to back that up. But if I only had a sample, meaning I use these 10 data to understand the rest of the company, well, there's a whole bunch of other people out there that I don't have data for. So it says don't divide by the total number, divide by 1 less. And so that's really how we think about the difference in the math. Most tools will just run this for you. When you're using a tool and it does a default, like you just run a variance or a standard deviation, it will almost always default to sample. That's probably a good default because most of the time we don't have all the data that we're working with. But just to know there's a little bit of a difference. But why does this stuff matter? So standard deviation, cool, 6.9, but how do we use it? Where does it actually matter? So let's say you're now in a role, you have to do some interviews. You're going to hire some people. You're super, super busy, and you don't want to spend your time interviewing a whole bunch of candidates because not everyone's going to work out. You just want to interview those that you think are better than average. You have candidates take a test, and you happen to know that the average on this test, which is a good test and really does assess the skills needed for the role, the average happens to be a 62. That's where the average person scores. You have 3 candidates. Candidate A scored a 76, candidate B a 71, candidate C 68. Who do you invite to interview? All 3? Just A? Just A and B? If the average is 62 and these are their scores, who do you invite to interview? Okay, maybe you spoke at your computer just now. Maybe you just picked A. Maybe you picked all 3 because they're all higher than the average. Well, a good response would be, I don't know, how good is 62 of a measure? Like, are most candidates really spread out, or do most score around a 62? That's where standard deviation could actually help you with this. If you knew that the standard deviation was 4, then you'd say, okay, most people score somewhere between a 66, which is the average plus 4, or a 58, which is the average minus 4. And that gives you a very different feeling about the numbers that you see here, because now all of a sudden, some of these candidates are falling into the most people bucket, and some are falling further outside of it. If you were told that the standard deviation was 8, that would change things even more. It would mean you'd have to score above 70 to be better than most people, and that you can go as low as 54 and still be like most people. Again, this would change very much where you felt that a candidate was strong. The thing we love about standard deviations is some smart people already spent a whole bunch of time saying that when data happens normally, and we'll just assume that we have normally occurring data, that we can actually say what percentage of the time we would expect a certain value if you tell me what the average is and you tell me what the standard deviation is. And so that's what these percentages here on the image are showing. It's saying that we can expect 68% of the data points to fall within one standard deviation on either side. So when I was saying that it was 4, we'd expect 68% of candidates to be somewhere between 58 and 66. Again, someone did the math, and 95% would fall between 54 and 70, and 99% would fall between 50 and 74. If we were told that it was 8, we could do the very same thing. You just change the number that you subtract and add. But the interesting part isn't in this, it's in how we think about our candidates now. So let's say you had candidate A who scored a 76. When the standard deviation is 4, here's where A is. But when it's 8, A is over here. So when it's 4, A is an amazing candidate. Oh my gosh, offer them a job now. This is so rare. But when the standard deviation is wider, you might expect this to happen more often. And so you'd feel very differently about your candidates. Same thing with B. And now when the standard deviation is 4, A and B feel like very different candidates. But when the standard deviation is 8, A and B kind of fall into the same bucket. So I don't know. And then same thing with C. So based on more information, you can make a different call. Again, no right answers, but if I knew the standard deviation was 4, I might definitely interview A, and I may or may not consider B. If the standard deviation is 8, I should probably assess both B and A, because they're kind of in the same bucket, and one of them may not necessarily be higher. Even though A scored higher, A and B might be the same if the standard deviation is 8. And so you would approach things differently when you know this information. And that's how it plays into the whole decision-making side. All right, another concept to kind of consider as we go into stats, and this is really important when we think about understanding whether or not what we've found can be treated as a true finding or not. And that's this notion of a hypothesis and a null hypothesis. A hypothesis is just something we think is going to happen. It's typically just written as a statement like, if I turn up the air conditioner, it will get colder in here. That's a hypothesis, and I can test it by using a thermometer to see if, in fact, the temperature did change. When you're assessing a hypothesis, there's always what's called a null hypothesis, and that's just that nothing happens. The null hypothesis would be, when I turn up the AC, there will be no change in temperature. That means no effect was found, no difference. In a business setting, you don't use the term null very often, but it pops up every now and then, so it's just worth calling out. You will hear hypothesis quite a bit, and that's usually just the thing you expect to have happen. One important kind of comment from the scientific thing is that you never can really prove a hypothesis. In fact, a way that you can test how well done an analysis is whether or not the person presenting it says that they've proven whatever it is. If you see the word prove, it's probably a marketing campaign. It's probably not real. In a hypothesis, we only ever have data that might support what we think is happening. And you can never truly prove it. You can only prove that there wasn't nothing happening. It's kind of a weird set of wording, but worth calling out just because it might pop up every now and then if you read a study or try to bring in some benchmarking or other data. But what you're trying to do with the hypothesis is you're trying to state whether or not the data that you have is indicating that this is likely happening and not just a result of chance. When we think that something is happening and not purely by luck or just chance, we call that statistically significant. Because analytics is kind of just smart guessing, it's an educated guessing, we always have a probability that we could be wrong and a probability that we could be right in what we found. It's especially true when you're working with sample data. Because again, we don't know what the rest of the data is. We got some data, and we're saying, well, if I got this with this data, then it's probably going to happen with the rest of the data. And we can run a little bit of math to say how comfortable or confident we feel that we can take what we found in this set of data and that it would hold true if we had all the data or if we gathered data multiple times. So statistical significance is just what is the probability that you would have gotten this same result by chance. And it gets used with different terms in setup, but the term statistical significance is just a statistical test to gather what is called a p-value or a probability value, if you want to think about it that way. And it's a value between 0 and 1, with 0 meaning that it was not due to chance at all, and 1 meaning this is just completely random chance. And so the number can be anywhere along that. We think about that number, that 0 to 1 number, as the percentage of being due to chance. So if you got a 0.5, well, that means it was 50% due to chance. It's really high. That means like could have gone either way. If you get a really small number, that means it wasn't likely due to chance. And when you get really small numbers, that's when you get to say, I think I might have support for my hypothesis. This statistical significance value, this 0 to 1 value, this p-value, is something that you compare to what's known as an alpha level. An alpha level is really just something you get to decide. It's the level at which you are saying that you would be wanting to not have your results be just due to chance. So if you're saying, I want it to be 5% or less of the time that what I found was just due to chance, you could say that you want an alpha level of 0.05. And the reason for saying that is if you're going to go do an experiment, you're going to run an analysis, you decide ahead of time what alpha level you want, and then you compare the p-value that you got to it. So if you say, I want to be having this due to chance alone less than 5% of the time, your alpha level is 0.05. Said differently, you might call it the confidence level. Confidence level is just the opposite of alpha. It's instead of saying, I want it to be due to chance less than 5% of the time, you'd say, I want to be confident 95% of the time. It's just the other side. So you can say it either way. You can say, I'm going to set an alpha level of 0.05 or a confidence level of 95%. I want to be confident 95% of the time that this wasn't just due to chance. And the most common alpha levels that people look at are usually setting it at 0.001, which means I want to be correct 99.9% of the time, or 0.01, which is I want to be right 99% of the time, or 0.05, which is the most common probably, saying I want this to not be due to chance 95% of the time. And you'll see that one probably the most when people ask about your p-value. They want to know, is it smaller than 0.05? And usually they want to know smaller the better. So the way I like to think about this, or try to remember p-value, is by showing you this adorable puppy here. So I don't know if you like dogs or not, but let's just say I have this puppy and I'm like, can you hold my dog for me for a moment here? Can I just set it on your lap? And feel free to answer at the computer. Will you hold my puppy? Some of you are going to be like, yeah, I love puppies, and you're going to like grab it and cuddle it. And then some of you are going to be like, I guess I'll hold it for a little bit. And then some of you are like, I really don't like dogs. So that is going to have a little bit of reaction in how comfortable or confident you feel in wanting to hold this dog for me. And then I'd ask you, well, do you still want to hold this dog for me? And those of you who wanted to hold it on your lap, you're going to be feeling a little funny. You're going to be like, I don't know, is it peeing right now? Like, did it just finish peeing? What's happening? So this peeing dog is how I think about confidence levels and statistical significance. Because we're all going to be comfortable with a different alpha level, depending on what we're doing, depending on the organization we work in, depending on where we're setting. You might set an alpha level or a confidence that's bigger. Maybe you're comfortable having it just due to chance 10% of the time, 20% of the time. Maybe you'd even set an alpha at like 0.2. That's going to come down to your own situation. So some of you are more happily ready to gather this dog up on your lap. But you're still going to assess the p-value. And when you think about P, think about it like PEE, like this dog. How much P are you comfortable having on you? For some dog lovers, you're like, whatever, it happens. Especially those with like, kids or puppies, like you're like, it happens, it's fine, whatever. For others, you're gonna be like, no, as little pee on you as possible. Usually you are going for as little pee as possible. And that's kind of how I like to think about the p value is usually you're hoping to have as little pee on you as possible, but always less than what you decided at the beginning that you were comfortable with. So decide the amount of being wrong that you're comfortable with. That's your alpha or confidence level. And then assess the p-value. Most stats packages will do this for you, and we won't expect you to do the hard calculations on it. But check the p-value. Usually smaller is better. So you're trying to get the smaller number that you can. So remember, p is like p. You want as little on you as possible. And a lot of different people will interpret different levels of p-value as more or less significant. This one on the right is just meant to be a joke. This is also where one of the questions kind of comes in. When you're going to look at p-values, usually 0.05 is kind of the industry standard. But if you're working on something where a little more confusion is okay and understandable, you can set it higher and that would be okay too. All right. Let me show you a very real example. I had something very similar to this happen to me once. I had a member of my team bring me a PowerPoint deck that had a slide very much like this on it. It said, oh my gosh, look at this. We are spending so differently on our employees that are based in Georgia than on Florida. And, this is a fairly common thing to have happen. And it was, we need to do something. What do we do? But if you spend some time with analytics, and if you know about descriptive and range and how we might think about things, you'd have a different response. You might say, you know what? I understand that this chart makes it look like we spend more in Georgia than Florida, but have we really? And do I have enough information to actually assess this? All I have are two averages. While the chart makes them look really different, like Georgia is twice as much as Florida. What's the range? What's the standard deviation? Are there any outliers? I need more information. So a stats response would take this a step further. And it might say, okay, I hear you. You have a hypothesis that we spend more on people in Georgia than in Florida. Why don't we go ahead and test that? So we might first look at the data. We might look at things like the mean, the mode, the median, standard deviation, the range. And I'm going to give you a second here to just look at these two sections. So Florida's on top, Georgia's on bottom. You can see the mean, which was what was on the chart, but look at the other data points as well. What do you notice that's different between the two sets? So you might notice that the minimum and maximum numbers are really different, especially when we look at Georgia, there being a maximum of 58, 53. Also, the range, really different. The variance and standard deviation, very different. This should tell you that the average might not be the best measure for understanding what's going on here. We might need to look into it more. Plus, we don't know if this is just due to chance. And so we might need to check whether or not this is a statistically significant difference between the two groups. And there is a way to test that. There's something called a t-test. And I put the scary equation on the slide only to show how complicated it looks. And then the written definition, just to say that all it's doing is saying, if I look at this average and I look at this average, and I take into account the standard deviation, how much each one varies, would they be likely to have overlapped and been this different just by chance alone? Or is this a really rare finding and there's probably real differences between the two groups? That's what t-test does. It says, cool, tell me the average, but tell me how spread out the data is. I'll go ahead and map them, and I'll tell you whether or not they're so spread out that this would happen likely again if you gathered new data in the future, or whether this is probably just due to chance. And so the t-test will run that math for you. And if you go to use a tool, you can do this in Excel, you can do this in any kind of interface, you can write up just a simple line of code. It will want to know, do you want to do a paired t-test or an unpaired t-test? And all it's asking there is, am I looking at data from the same source at like 2 different times or 2 different points, or am I looking at data from 2 completely different sources? And the reason it asks this is because if data comes from the same source, like it's coming from the same person at 2 different times, well, each person tends to have the same kind of variance because they're still that same person, it's just different time. Versus if it's coming from 2 completely different people, they might have a really different starting point. And so paired just means same data source, maybe 2 different instances. Unpaired means these are coming from totally different places. Since Georgia and Florida employees are different employees, we would call this unpaired. So we'd ask whatever tool that we're using, hey, can you run me an unpaired t-test so I can compare Georgia to Florida and see if they're statistically significant? And we'll get kicked out a little response. There is a how-to video on how to create this output. In your class links, there's a little YouTube video. But basically, you'll get a p-value. Again, a p-value is anything from 0 to 1. And the smaller the better, as little p on you as possible, but at least less than whatever alpha level you set. We're going to go with 0.05 because that's kind of an industry standard. And then we'll look at the p-value and say, is it smaller than 0.05? And in this particular example, we're finding that the p-value is not. It's bigger. That's more p on us than we are comfortable having on us. So we would say, no, this is not a statistically significant difference. And that really informs how we would talk about it. We'd say, yes, I know this is how it looked on the chart, but when we look at the data, we see that the difference, even though there is a difference, is not statistically significant. There's an almost 18% chance. What I did there was take the p-value from the last page of 0.1768, just kind of rounded it up and called that 18%. 18% chance that we would have found this much difference or more if we ran the data again and ran it other times. So while there is a difference, it's not statistically significant. And in fact, I'd probably take all this information and talk about it in a different way. I probably wouldn't use that misleading averages chart. I might look at the fact that even though there were differences in averages, the median tended to be about the same. The middle point was about the same, or I might just talk about them in a different way altogether, maybe showing their distributions. So all of these are good ways to go from this assumption that there are differences and check them for something like statistical significance. All right, our last concept here for this is really getting into this idea around measuring relationships between variables. That last example was there a difference? Was Georgia different than Florida? But a lot of times we're looking at relationships between or among different sets of data. Correlation, very popular. Most people kind of intuitively know what correlation is, but it's a measure that just says how, when one variable moves, does another variable tend to move with it? Does it tend to also to go up, or does it tend to go down as the other one moves? It's also a measure that can be thought of as 0 to 1, but it can go from -1 to +1. When you get a value of 0, that means there is no correlation. When you get a value of -1, that means that as one variable goes up, the other one tends to go down. When you get a +1, that means as one variable goes up, the other one tends to go up. So to give you kind of an example here, you might have data on employees, and maybe you have manager satisfaction score. Employees are asked, how satisfied are you with your manager on a scale of 1 to 5? And they indicate their scores. And then you also ask, how engaged are you at work? 1 to 5, and they indicate their scores. You could then run a correlation to say, as one of these goes up, say manager satisfaction, does engagement tend to also move at the same time? And if you were to plot each one of these dots, you'd get a picture that looks kind of like this, with this being an employee who rated their manager as a 1 and their engagement as a 2, and so on and so forth. We can essentially draw a straight line through that and say, does it appear that as I go to the right, the other thing tends to go up or down? And if so, to what degree? This is what the correlation will do for us. In this particular instance, we get a correlation of 0.735, and we can say that because it's positive, as manager satisfaction goes up, engagement tends to go up as well. Or said differently, as engagement tends to go up, manager satisfaction tends to go up. It doesn't imply which one happens first. So 0.735 by most assessments would be considered a high correlation, but there is variability in what's considered a strong correlation. This is just two different tables that talk about different levels. You'll see the values are actually set at different markers. One says it's not high until it's a 0.8. The other one calls it high at a 0.5. These are just different ways that you can think about it. Usually provide your correlation value along with maybe your verbal description of whether or not you see this as moderate or low. In people analytics, you won't see as high of correlations just because people factors tend not to be so simple. They tend to have a lot more going on, so you might see lower correlation values. Sometimes a 0.3 is actually considered worth discussing, whereas in other sciences that might be considered quite low. So simple correlation is great. It says as one thing moves, does the other one go, but it only does that in a straight line. Not all relationships follow a straight line. Here's an image where there's a first image where it's going to be explained very well by correlation. As one goes up, the other one goes up. But if you have a slope or a U or even kind of a squiggly S, correlation's not going to identify that. So I always recommend plot it first, because I would call these pictures very clear relationships. Like there is something going on here, but that straight line's not going to show up for you. So just because you run a correlation and you don't get a really high value, don't think that doesn't mean there's no relation. It just doesn't mean there's a simple straight line. Some other things to consider with correlation is it does not equal causation. It doesn't say which one happened first. It only says that they are co-related. So it gives covariation, meaning as one moves, the other one moves, but it doesn't say which one happens first, and it doesn't control for other things. So a great example here is a very real correlation. This is real data. This is a very funny website if you want to check it out, Spurious Correlations. And it is very real data on very real correlations that are statistically significant. And here, for example, is the number of people who die by becoming tangled in their bed sheets is very strongly correlated with how much cheese people eat. And that is a weird correlation. I love cheese. I own bed sheets. This would be scary to me if correlation equaled causation, but it doesn't. And especially in our applied settings, we have to be careful when we find a correlation not to imply that it necessarily leads to it. There might be something else going on or causing it. Now, correlation, very related to regression. If you've ever run a correlation, you've actually done regression. It's the same exact concept. It's all connected. Regression is just a technique for determining the same relationship, same linear relationship, with the only difference being that we think one thing came before the other one. So a correlation says, okay, as one thing moves, does the other thing happen to move? Regression says, if I move one thing first, will the other thing then move? The way we run it in the data is actually very, very similar. So the concept between correlation and regression can be thought of as basically the same thing. In fact, you run a simple linear regression the same exact way you run correlation. You just usually gather a couple more information. But you have to first set, is one of them happening first? And is one then the outcome, the thing that happens in the end? The outcome variable, the thing that is changed, that we're trying to predict, that we're trying to see what happens, is what we would call the dependent variable, meaning it's going to change depending on the other variable. The other variable is called the independent because it can do whatever it wants. It kind of comes first. It leads to the other change. So we call it independent. Think of it like your really independent friend who does whatever they want. But then there's like your dependent friend who will only go if like you go. That's kind of the same thing with how we think about it in a regression model. You've got your independent variable that makes things happen, your dependent variable that is affected by whatever the independent variable is doing. And so with that same exact data that I showed you earlier, manager satisfaction score, engagement score, the math is identical when you're running a regression on it versus a correlation, at least when you're only working with these two variables. But we can say that we think one leads to the other. So we think how much you like your manager, the manager satisfaction score, leads to how engaged you are. So we would say that manager satisfaction score is the independent thing and predicts, causes, or leads to employee engagement. And that direction helps us then talk about it in a different way. It lets us use it to predict the other one. So you can almost say, if I know your manager satisfaction score, to a certain degree, I might be able to predict your engagement score, assuming that there's a relationship. You also could use it to say, how well can we predict the relationship? So the way you might read a regression outcome is you take this thing called the R-square. This is something that is actually the correlation coefficient times itself. The correlation coefficient is R. R squared is just correlation coefficient times itself. So if you want to have fun for a minute, you could take the correlation coefficient, went too far on my pages, that we got on our page, and you can multiply it by itself. So it was 0.7 something. I've lost my pages, sorry for moving around. Multiply it by itself, and you're going to get the R squared value that pops out of 0.54. And the R squared value is really useful in talking about the amount of variance or change in the dependent variable that can be explained by the independent variable. So we can take the value that comes out in the R square and use it in a sentence to say how much we think manager satisfaction predicts or influences employee engagement. And in our particular example, our R square was a 0.54. And so we can say that when we think about manager satisfaction and its impact on engagement, we can explain 54% of the variance in engagement by knowing the value for manager satisfaction. That would actually be huge. To know 54% of why an employee is engaged just based off of how they feel about their manager, it'd be a very useful statistic and piece of information to have. I am so sorry, I just lost all of your... Please give me one break. I will try to cut this out of the video, so apologies everyone for a bit of delay there. My slides went haywire. So when we have this R squared, we're able to explain how much of the dependent variable is explained by the independent variable and how strong our model is. So a bigger R squared value usually means a stronger, more descriptive way to talk about what we would expect to be happening. The other thing that we like about having the R square is just the ability that it gives us to talk about what we know and what we don't know. So said differently, if we understand that 54% of engagement is explained by manager satisfaction, that still leaves 46% that we might need to figure out through other means, maybe with other analyses, other ways of approaching it. And we can use the values that come out of regression in really powerful decision-making ways. So if I have my data set that I showed you, and if I'm trying to predict employee engagement by using manager satisfaction, and I just ask a tool like Excel or R or Python or SAS to run the analysis for me, I can get the kind of information to answer these questions here. So I can know just from the output that for every one increase in manager satisfaction, that's the X variable, that I can expect my engagement score to go up by 0.75 of a whole point. Now this is a 1 to 5 scale, so this is actually a big deal. And I can say that for every one increase in manager satisfaction, my dependent thing will come out 0.7 higher. The reason I know this is because the equation says every time you get an x value, multiply it by 0.75. And because this is a y equals equation, every time you get a bigger value, the y is going to come out bigger. Y in our case here is meant to be engagement. So we can play that out pretty well. And because we have the R square, we also know that when we use this to predict what someone's engagement might be, that we know about 54% of the variance is explained. There's still other stuff going on, but we've covered quite a bit just by knowing this. And we can use this really simple set of data to even do things like forecast and predict what's going to happen. So if I know what an employee's manager satisfaction score is, I can use this equation and just plug it right in and predict what I think their engagement score would be. So if I take my value of 4 and I put it where the x was, and I finish the equation out, I'll know that 0.75 times 4 plus this constant, 1.25, equals 4.25. And this lets me predict what's going to happen. Now, if this was a little rough for you here, there is a how-to video all walking through your correlation and then also regression and how to read the output. So I definitely recommend watching that how-to video. But the importance here is we can make decisions with something as simple as this equation. If we have a new employee and we're looking at what team to put them on, we know that if we put them in a team where the manager satisfaction score is higher, well, their engagement is likely to be higher. But if we put them on a team where the manager satisfaction score is lower, well, their engagement score is going to be lower. And if we're worried about, say, attrition of new hires, this might really affect where we might place a person onto a new team if they're a particularly talented or, a individual that we are particularly keen on seeing progress and move through the organization. So we can make decisions by having this data in our hands. Now, one comment I'll make is a lot of people, when they build regression, they love that R square. What percent, however big it is. In people analytics, you might have some low R squared values, and you will have to ask yourself, given what I'm studying, is this enough of an R square? So 0.54 is huge, and that would be great in people analytics. Sometimes you're going to get a model that has an R square of like 0.03. In most sciences, that would be too low to do anything with. And in fact, you might decide that for what you're doing, that's too low to do anything with. But what you want to do is you want to pause and you want to think about how you're applying it and say, okay, that means I only know 3% more than what I did before. In most cases, 3% is probably not worth the investment or the effort. But if it was a 0.1, maybe 10%, while not a big number, is enough to make it worthwhile. You really just want to think about the applications and whether or not that R square is of value for the business decision that you need to do. And also, don't always assume that a high R square is going to mean that it's incredibly valuable. It can just mean that this particular pattern is very strong, but that doesn't necessarily mean that you'll be able to do anything more effective with your decisions. And with regression and correlation, you should always still be checking your statistical significance. So you want to check your R square. Is it helping to explain a lot of the thing that I'm trying to explain? And if it is, will I get the same result, not just due to chance again? So you need to check your R square and your p-value. Again, as little p on you as possible, and below whatever alpha level you set. So what I just covered here is simple linear regression, and then there is multiple linear regression. What multiple linear regression will let you do is just to put an additional variable in there. So sometimes managers aren't the only thing that leads to engagement. Maybe how much you get paid, maybe your work hours, all sorts of other factors. You can still add more variables, and you've got an Excel video that will show you how to add additional variables if you're doing it in Excel. If you're doing it in other programs, it just means in addition to adding that manager satisfaction, you could add multiple other variables. You will always only have one dependent variable, but you can have as many additional independent variables as appropriate. You just want to make sure that those individual variables are statistically significant inside the model. And you would check that with p-values on each of your variables. And you check that that is still working. And you can always take variables out, add them in as you try to build models. We'll get more into building the models as we go, but just know there's a multiple stage. I'm not going to cover logistic right now, but we will also get to the point where we talk about logistic regression, which is really just saying, what do I do if my data is just binary, meaning yes or no? Took the job, didn't take the job. Passed the class, didn't pass the class. There is a form of regression that lets you assess things that are just two categories. And so we'll get into that as well. But for this purpose, for right now, we are going to call it at that. You've got lots of how-to videos. You've got lots of pieces that help you. You've got resources. You can reach out to me, TA. We're all here to help you. But this should at least get you started. And good luck. You got this.